Hey guys, myself Dhruv Patel, your tutor, your friend, your lecturer who teaches you daily in the lecture of design of structure, and I'm very happy that you all watch my videos and you like my teaching. I hope you all understand how I teach, how I make you understand. Okay, so today with another video. In this video, we will study about design of one-way continuous slab. Okay, so let's start. Here I have given one example. Here it is written that design a one-way continuous slab which is of 3 equal span, which has 3 equal span of 4 meter, and the live load is given 4 kN per meter square. Floor finish is given 1 kN per meter square, M20 and Fe250. Okay. In previous video, we have studied about simply supported one-way slab. Today we will study about a continuous one-way slab. So let's see how it is differ from the one-way slab, means simply supported one-way slab. Okay. So 3 equal span. It means the figure will be like this. This is 1, this is 3 span, all of 4 meter. In continuous slab, we have to take the center to center support distance. Okay, so the motto is only same as per the previous sum. The motto is like we have to provide AST, for that we need to PT, for that we need moment, and for that we need W, and for that we need size. Here we have our length. So the step is same as the simply supported one-way slab. The difference is only while finding the moment calculation. Okay, the equation of moment is changing. It is only the thing that changes in the sum. Otherwise, the whole step is as early as today. Okay, so like we will take the step 1. Step 1 is what? Step 1 is effective depth. Effective depth means small t. Okay, so for that we were taking the span by depth ratio, L by D. Okay, and here I have explained you that 7 for cantilever slab, 20 for simply supported slab, and 26 for continuous slab. So here it is all continuous slab, so the value will be 26 into MF. We need to find the depth. So the equation of D is equal to L divided by 26 into modification factor. The length is nothing but the 4000 mm, and modification factor will be as per the page number 38, as per the chart. So the percentage of steel we will assume is 0.6. Okay, something like 0.6. The percentage of steel we assume 0.6. And remember one thing, here it is given mild steel, Fa is equal to 250. So the in equation of Fs, which is 0.58 Fy, the value will be 0.58 into 250. So it will be 145 Newton per mm square. So regarding to this, on the basis of chart, the modification factor value is 1.8. So the depth will be, let's calculate, 4000 divided by 26 into 1.8. It is 85.47 mm. Which is very low. So in round figure we will provide our depth is 120 mm. It should not be less than 100 mm. Okay, remember that. Now we get the value of effective depth. On the basis of effective depth, we will find the overall depth. Overall depth means capital D. Likewise, I show a figure in the diameter 10 mm. If this is our effective depth, then this is the diameter by 2 and this is the clear cover. So, the overall depth will be D plus diameter by 2 plus clear cover. It will be 120 plus 10 by 2 plus clear cover. Suppose you are taking a 10 mm diameter here, but after calculating the moment, the possibility of taking the 10 diameter is less. At that time, if you wish that I want to take 8 mm diameter, then you don't need to change the overall depth value, because the overall depth value is being selected on the basis of maximum diameter. Okay, so the value will be 120 plus 5 plus 20. So overall depth is nothing but the 145 mm. Okay, so the step 1 is clear, and step 2, the span is foot meter itself, so we doesn't need to calculate the effective span. So moving to the step of load calculation. So I am mentioning here that our effective depth is 120 mm and overall depth is 145 mm. So moving towards the load calculation. Okay, so first of all we will take as a self weight dead load, which is 0.145 into 1 into 25. It will be like 3.625. Second one will floor finish load. It is 1 into 1, so 1, which is provided here. Okay, 1 kilonewton per meter. Now here we need to separate both load, the dead load and the live load. Why? I will explain you later. So floor finish is one type of dead load, so it will consider in the dead load portion. So total load is equal to 4.625. So factored dead load is equal to 1.5 into 4.625, which will be 6.937 kilonewton per meter. Okay, and the live load is 4 into 1, which is 4 kilonewton per meter. So factored live load is 6 kilonewton per meter. Okay. So after calculating the dead load, another step is come, which is to calculate the bending moment. Okay, because size we have calculated and load also we have calculated. Now going to the another step, which is bending moment. So in one way simply supported beam, we were calculating the bending moment by the equation of WL square by 8. But in this, the load is spread all over here. Like this. it is dead load, which is 6.937 kilonewton per meter, and live load, which is 6 kilonewton per meter. Okay, why I have separated the things? Because the coefficient for fixed support, the moment will occur here at the support also. Let me explain you. In simply supported slab, if the support is simply, so the moment will not occur on the support portion. But if it is continuous, then this support will become fixed. This interior support will become fixed. So at that time, the moment will occur on this support, this board support. So the diagram of this will be like this. Bending moment diagram. At support it is 0, but at interior support there will be some moment, which is upward moment. It is also known as hogging moment. It is in minus, and this one will be in plus. So for this, the coefficient of bending moment are provided in IS 456 page number 36. This is the table for bending moment coefficient. Okay, so the coefficient is divided in dead load and live load. The first line of coefficient will shows the value of dead load, and the another one will be for the live load. Okay, so by this bending moment coefficient, we need to calculate the bending moment. So let me explain you in detail. And in book, the calculation is done separately, but I will take some easy method. Easy in the sense I will take the method of a table form. Let me say you that how the table form is being used. Okay, so remember the thing, the dead load is our 6.937. Let me write this, 6.937 kilonewton per meter, and live load in the sense is 6 kilonewton per meter. Okay, so it is very easy. Nothing is hard to solve. Okay, everything is very much easy. So first of all, I am drawing the figure. The figure is like this. This one is our one-way continuous slab. Okay. This one is our first support. This one is our second support. This one is our third support. And this one is our fourth support. So I will name it label like A, B, C and D. Okay. The overall UDL load is occurring like this. Which is the combo of dead load plus live load, or separately I can say that dead load and live load. Dead load which is 6.937 and the live load which is 6. I will make the table. Understand it well, focus while I am teaching, because I am teaching you in a very easy way today. So Most probably I am teaching you in easy way, but today is very much easy. I am making this sum so much easy. In first row, the coefficient for dead load. Okay, dead load. So, as is shown here, there are two columns. The first one is showing span moment and the another one is showing support moment. In span moment there are two types. The first one is showing near middle of end span, and this is all at middle of interior span. So let me write you mid span. So I am making you A, B, C, D. So I am considering the A, B, C, D as support moment. What? A, B, C and D as support moment. Okay, and I am naming the mid span E, F and G. So E, F and G as span moment. So it will be easy to understand. Okay, E, F and G as span moment. So the span moments meet at middle and the support moments meet at support. So the A is simply support. So here the coefficient will be 0. And D also simply support, so it will be also 0. Okay. First of all, we will complete the span moment. So span moment, this is the end span. So what it is written? Near middle of end span. So middle of end span. So the coefficient is plus 1 by 12. What? Plus 1 by 12. So this is also near middle of end span. Middle of end span. So it will be also plus 1 by 12 for dead load. Okay. So this is a at middle of interior span. This is the interior span. It between two end span, so it is the interior span. So what is the coefficient? It is plus 1 by 16. Okay. So we have completed the span moment coefficient. Now for live load. Live load also this is 0. So live load is the second one. Plus 1 by 10. Near middle of end span. So it is also plus 1 by 10. And interior span plus 1 by 12. Okay. Now coming to the support moment. The support moment at support next to end support. This support is next to end support. So this is next to end support. So the coefficient will be minus 1 by 10. So this is also next to end support. So it will be also minus 1 by 10. The another column is at other interior supports. Means if the support is between here, then it will be the interior support, not next to end support. So now writing the live load coefficient is minus 1 by 9. If we have 4 span, then we will have the interior support. But here only 3 span. That's why we doesn't have an interior support. So 0 and 0. So I hope you all understand how the coefficient we have to take. Now this row also completed. Okay. Now it is very simpler. So moment of dead load. This is 0. This is nothing but the, as we have taken in simply supported WL square by 8. Simply supported one way slab. In here we just have to put WL square in the place of 1. L is nothing but the 4 meter. Okay. So we have to put only for dead load. Moment dead load means only we have to take dead load coefficient and only we have to take the dead load. So W L square by 12. So dead load was 6.9375 into 4 square divided by 12. So the value will be 9.24 kilonewton into meter. Okay. Likewise, here also we have to take W square by 10, W square by 16, W square by 10, W square by 12. So here it is 9.24, so here also it will be 9.24 kilonewton into meter. Let me solve it very fast. So 6.9375 into, here also, but the value will be minus. If you don't write minus, then it is not problem, because minus sign shows the hogging moment and plus sign shows the sagging moment. Okay, so W square by 10, 11.09 kilonewton into meter. Here also it will be 11.09 kilonewton into meter. This is 6.937 into 4 into 4 divided by 16. So it is 6.937 kilonewton into meter. Likewise, take the moment of live load. This is 0. And here live load is 6. So WL square by 10. So 6 into 4 square divided by 10, which will be 9.6 kilonewton into meter. Likewise here, remember one thing, don't mix up two coefficients. Okay? Verify. 6 into 4 into 4 divided by 9, it will be 10.66 kilonewton into meter. Here 6 into 4 into 4 divided by 12, it will be 8 kilonewton into meter. This will be the same 10.66, and this will also be same 9.6 kilonewton into meter, and this will be 0. Okay, so we have find the particularly dead load moment and live load moment. Now the next row will be total moment, mu, which will be sum of these two. So 9.6 plus 9.24, 18.84 kilonewton into meter. Here it will be 10.66 plus 11.09, 21.75. Here it is 14.937. Here it is 21.75, 18.84, 0. Okay. Now the question will arise, why we have mixed up this whole thing. Okay. So the difference was that the coefficient for moment was different for dead load and live load. So we need to calculate the moment particularly for dead load and live load. After that we have to mix up both moments. Okay. After calculating that, now find the after moment, we need to calculate the PT. So the percentage still, as we have find is the by using the equation of 50 XUK by Fy. Let's calculate the PT. So I am taking you the first one. The equation was like this: 50 FCK by Fy and 1 minus under root of 1 minus 4.6 mu by FCK BD square. Okay, B will be 1000 and D will be our effective depth, which is 120. So let's calculate the PT for this. So 18.84 into 10 raised to 6 into 4.6 divided by 20 into 1000 into 120 into 120. 1 minus answer under root of answer, 1 minus answer into 20 into 50 divided by 250. Okay, so PT is 0.65 percentage. Remember one thing, our Fy is 250. In the flow we will take 415 because we generally solve the example regarding the 415. That's why. So here 0.65, here also will be 0.65. Okay, now calculate this one. So this one PT will be 10 raised to 6 into 4.6 divided by 20 into 1000 into 120 into 120. 1 minus answer under root of answer, 1 minus answer into 20 into 50 divided by 250. So the answer will be 0.76 percentage. Here also it will be 0.76 percentage. The last one, which is 0.50. Okay, so we have calculated all the percentage of steel. Now calculate the AST. So our next step will be to calculate the AST. So AST is nothing but the PTBD upon 100. So let's take the 6.65 into 1000 into 120 divided by 100. So this is 780 mm square. So here also will be 780 mm square. Now here 0.76 into 1000 into 120 divided by 100. So it is 912 mm square. Here also it will be 912 mm square. Now this one 0.5 into 1000 into 120 divided by 100. So here it is 600 mm square. Okay, so we have calculated the AST. Okay, it is easy. So now we have to provide the AST spacing. But before providing spacing, I will show you how the reinforcement is being placed in the figure. Let me rub this thing so that I can show you in figure. So our figure will be like this. This will be our A point, this will be our B point, this will be our C point, this will be our D point. This will be our E point, this will be our F point, this will be our G point. Okay. So first of all we will provide the span moment. So spacing for all the member we will take the diameter of 8 mm. Take diameter of 8. Okay, for all the bars. Okay. For hogging moment also as well as for span moment also. So first of all we will provide for this spacing is equal to small AST by capital AST into 1000. Okay, so small AST is pi by 4 8 square. So 3.14 into 8 divided by 4. So it is 50.24. So spacing is divided by 780 into 1000. So spacing is 64. Is 64.4. Wait 1 second. So the spacing is 64.4. It is getting so much lower. So let's take the diameter of 10 mm. So for that it is 78.5. So now find the spacing. 78.5 divided by 781 into 1000. So it is 100.51. So provide 10 mm dia of 100 mm center to center. Okay. So 64 we can provide, but it is providable. Okay. So this is also 10 dia 100 mm center to center. Now midspan 600. So 78.5 divided by 600 into 1000. So 10 dia 130 mm center to center. Now we will provide the reinforcement first of all. So this one reinforcement of V will be start from here and will go from here to here, and from here it will be start, and from here it will go here to here. This is 10 dia 100 mm center to center. Likewise this will also, from here it will start, from here it will go up to here, and from here it will start, and from here it will go up to here. So this is also 10 dia 100 mm center to center. Okay. The middle one 10 dia. So it will be start from here to here, and from here it will start and go from here to here. This is 10 dia 130 mm center to center. Okay. So I want to explain like you that here we need 912 mm square AST, but we see here that this bar start from here and the half bar is ending here. So the half reinforcement of 780 is on the hogging portion. So 780 by 2. So here we get 390 from this side, and here it is 600. So half 600 is coming here. So 600 by 2 means here it is coming 300. So total we are getting 690 mm square. We needed 912. So from the 912 mm square, the 690 mm square AST we are already getting from the E reinforcement and F reinforcement. So we need to provide the reinforcement for the remaining part. So the remaining portion is 912 minus 690. 912 minus 690 is equal to 222 mm square. So we need to provide the bar for the remaining portion, because already this reinforcement is going in the bent up way towards the hogging portion. That's why the half AST is coming here from here and half from here. So we have to provide 222 mm square. So 785 divided by 222 into 1000. So the spacing is 10 dia 350 mm center to center. Here also it will be same, 10 dia 350 mm center to center. Okay, I hope you all understand that what we have to do here. Okay, we doesn't need to provide 912 because it will be overweight and the beam will fail, because already we are getting 690 mm square from the midspan to the hogging portion. So why we put extra 912? Okay, so it will become so heavier. Okay, now we have provided the spacing also, and the last form is distribution steel. So distribution steel is same for all, so we will calculate it in common. So for distribution steel, oh wait, we need to provide this. So here it will be start from here to here. This will be the hogging moment bar. This both is 10 dia 350 mm center to center. Okay, now we will provide the distribution steel is of minimum percentage of steel. which is 0.15 because we are taking Fy is equal to 250. So AST is equal to 0.15 B into 1000 into capital D means 145 divided by 100. So the value will be 217.5. Okay, and spacing will be for 6 mm dia. Okay, for distribution is 6. So 3.14 into 6 into 6 divided by 4 divided by 217.5 into 1000. So 129. Here the 350 is the maximum of the 300. So we need to provide 300 instead of 350. Let's explain this thing. Okay. So here it will become 300 because it is main reinforcement, and for main reinforcement spacing should not be increased than the 300 mm. Okay. So 129 means 10 dia of 6 dia of 125 mm center to center. Okay, which is provided like this. It is common for all. So all the distributions still are 6 dia 125 mm center to center. So this is our one-way continuous slab calculation. We have calculated both main reinforcement and distribution reinforcement. We have calculated spacing of both, and we have shown in the figure like this. This is our figure. This is our overall depth, which is 145 mm, and this is our effective depth, which is 120 mm, and this is our 4 meter slab. Okay, like this we can draw a figure of the one-way continuous slab. So this is our design of one-way continuous slab. I hope you all understand it very well. If not, then comment me. Okay, up till that. So we will meet in next lecture. Till then, take care. Bye bye.